So last time we talked about think about these functions in geometrically as like a parent function, then a transformation of the parent, right? And we saw that we could take these geometric ideas of like translation and reflection and dilation and apply them to an algebraic setting. And what we're going to do now today is we're going to take our sine cosine operations and turn them into a function, and then apply those same transformation ideas to our sine cosine functions that we developed today, and talk about culminating in like how do I graph any sine function or any cosine function in kind of the most straightforward way possible. Okay? So in chapter 2, like the big idea was we took sine and cosine from operations in geometry that worked on only angles between 0 and 90 degrees and expanded the definition to where we can do sine and cosine of any real number, right? No matter how big or small the angle is, that's an angle that we can draw on as a standard position angle on the XY axis and find its position on the unit circle potentially and evaluate sine or cosine from it, right? So what we're going to do here is we're going to take points for the sine function from the unit circle. So for our sine function, the inputs are going to be an angle measure, and the output would be sine of that angle measure. So the x's, the inputs are our angle, and our output is going to be the sine of that angle. Everybody's okay with that? So the question that comes up, since we're talking about angles, is are we going to do this with degrees or radians? Which version of our angle measurement do we want to use? The answer, unfortunately for you, is we're going to use radians. The reason we do that is because 2 pi, one rotation around the unit circle, 2 pi is a little bit more than 6. So that means potentially like 6 tick marks on my graph. 360 degrees is one rotation. That's 360 tick marks on my graph. Stab me in the eye, I don't want to do that. That's why we tend to use, the convention is to use radian rather than angle measure. Everybody's okay? All right, so let's start plotting some points from the unit circle and see what this sine function is going to look like. So our angle measure, we're going to start here at 0, and then sine of 0 is the y coordinate on the unit circle. So our first point is 0, 0. The next point is pi over 6, and then sine of pi over 6 is 1/2. So my next point is pi over 6, comma 1/2. Let's pick a better color that's a little bit easier to see. Let's do this like neon green. So you see as I'm typing the points in, they're coming up on the graph, right? The next one is pi over 4. And sine of pi over 4 is square root 2 over 2. As a decimal, that's basically 0.707. The next point would be pi over 3, and then square root 3 over 2. Square root 3 over 2 is 0.866 approximately. And then we have pi over 2, and the sine of that is 1. So we're just kind of graphing points on our sine function right now, right? That's all I'm doing is taking my unit circle and getting my points for sine function. So the next one is 2 pi over 3, and then root 3 over 2. And we just kind of keep going. So 3 pi over 4 and 0.707, and then 5 pi over 6 and 1/2, and then pi and 0 again, and then we have 7 pi over 6, and this time we have negative 1/2, right? Because we have, again, we're using the y coordinate from the unit circle as our value for sine. Next one is 5 pi over 4, and we're negative 0.707. And then we have 4 pi over 3, and we're negative 0.866. And then we're at 3 pi over 2, and we're at negative 1. We're just kind of continuing along, just putzing along the unit circle here. Putz, putz, putz. So I'm just going to kind of keep typing these in. So there's our picture. Everybody's okay there? So if we look, just say y equals sine x. Oops. So that's what the curve looks like. What's going to happen though if I kept going around another time? Like I did 13 pi over 6, and I'd be at a half, and then I do 9 pi over 4 and 0.707, and 7 pi over 3 and root 3 over 2. What's going to happen if I just go around another time? It's just going to give me another one of these like up and downs, right? Let's just kind of see that. So we'll go 0 to 4 pi. We'll do one more loop around. Everybody's okay with that? What if I did another loop around the unit circle? What am I going to get? It's exactly what you think happened. You get another, like one of these up and down cycles, right? So what we're going to see is that this function just repeats itself over and over and over again forever. And if you wanted to go backwards around the unit circle, it would repeat itself, along the negative part of the x-axis as well. A function that repeats itself like this is called a periodic function. So sine and cosine are examples of periodic functions. And a function like this that makes like a wave, that's periodic like this that makes a wave, is called a sinusoid. Just some like light vocab for you. So let's kind of pack this together and give a little bit of info dump now about what's going on. So we're going to first start by just kind of talking about the sine function now that we have an idea of what it looks like. So the sine function, we're going to say the parent function version of it is just f of x equals sine x, or y equals sine x. The domain, since we can input any real number in for sine and do that problem, the domain is all real numbers, right? We can do sine of any angle now. The range, if I look at my graph of my sine function, the lowest value, or the lowest point, has a y-coordinate of -1, and the highest point has a y-coordinate of +1. So my range is going to run from -1 to +1. Why did I use brackets on the range rather than parentheses? Do you remember what the difference between the bracket and parenthesis was from chapter 1? I didn't. Great, yeah. The bracket means included because we actually have a point whose y-coordinate is -1, and there's actually a point whose y-coordinate is +1, right? Those are points, or those are coordinates that are used by points in our function. Everybody's okay with that? Okay. We say that this has odd symmetry. If you remember from chapter 1 when we had like if I compared kitty corner across the origin, if the function was the same, that was what odd functions looked like. So we can see that that has odd symmetry. We say this is continuous because if I draw the graph, I can do it without having to pick up my pencil, right? And then we have this terms for amplitude, midline, period, frequency, and then some values here. Let's explain what those things mean. This is the window I'm looking for. So let's just grab one of these. So I'm going to just kind of draw a picture to describe what amplitude, midline, period, frequency is first, and then we'll define them in words here in a moment. But I want to do it visually, because I think that's just like, the words can be kind of hard to understand sometimes. All right, so I'm going to start with the midline. Basically what the midline does is it divides the graph in half vertically. So I want half of the graph above the midline and half of the graph below the midline. So the x-axis here, or the line y equals 0, would act as our midline. Everybody's okay with that? We can see that there's equal amounts of the graph above and below the y-axis now. Or x-axis, excuse me. So far, so good? The amplitude is the distance from a extrema, so a max or a min, back to the midline. And that distance will be the same whether you're going from a maximum or from a minimum back to the midline, because the humps are the same height, right? So we said that this is a periodic function because it repeats itself. The longest non-repeating segment of our graph is called a period. So like if I go from here, I do an up, and then I do a down, and I end back at a midline. So that's like one cycle of my graph. The distance on the x-axis that it takes for one cycle is a period. So that horizontal distance that it takes to complete one cycle of my graph is a period. Everybody's okay with that? And then the frequency, give me a new color, is like how much of your period do you complete in 1 unit on the x-axis. So like x equals 1 would be like right here. So this much of the graph we've covered in side of 1 unit. That is like 1 pi over 2th of our graph. Right, 100% of a cycle would be 2 pi. We did 1 out of 2 pi. So it's like, a little less than a sixth of the graph. But that's what we're talking about when we talk about frequency. Okay with that? All right, I'm going to go and info dump the cosine stuff because it's basically the same thing, except the graph looks slightly, ever so slightly different. And then I'm going to dump in the word definitions for sine, or for amplitude, period, frequency, all that jazz. All right. So if I look here at the information for cosine, notice everything is the same except for the symmetry, right? That's the only difference. Cosine has an even symmetry because if I look at the graph looks a little bit different, right? The big difference here is that cosine starts at a maximum, whereas sine starts on the midline. But other than that, it's the same picture. It's basically the same graph. It's just been shifted, depending on your perspective, left or right some amount. Everybody's okay there? And so our word definitions now for amplitude, midline, period, and frequency, I've put in there. So amplitude is half the total height of a wave, so half the distance from a max to min, which is the same as the distance from an extrema to the midline. I like thinking of it that way because it's just a simpler way of saying it. The midline, again, is like cuts the thing in half. So it's halfway between the minimum and maximum y values. The period is the length of one full cycle. And then the frequency is the number of cycles completed in 1 unit interval. So frequency and period are like definitionally reciprocals of each other. So the frequency is always going to be 1 over the period. So far, so good? Okay. So what we've done so far is we've now created and formalized a function for sine and cosine. And we've talked about some attributes that those functions have, some visual attributes, the amplitude, the period, the midline, the frequency, all have to do with visually what the graph looks like, right? What we want to do now is take that idea of a parent function and resultant function and apply it to the sine and cosine graphs. So let's go and do that. Let me just drop that in here. So we say a function is a sinusoid if it can be written in the form f of x equals a times sine of 1 over c times x minus h plus k, where a, c, h, and k are all real number constants, where a and c are non-zero. We can treat as parent functions y equals sine x and y equals cosine x, and as a result, f of x equals a times sine 1 over c times x minus h plus k will be a resultant transformation of sine, and g of x equals a times cosine 1 over c x minus h plus k, a resultant transformation of cosine. So again, this is the same idea that we talked about last time, right, with a parent and resultant. What's the only difference between what we did last time and this time? Before, we were talking about a general f of x as our parent function. Here, our parent function is specifically sine or specifically cosine, but otherwise it's the exact same ideas. So, seeing that these transformations or these resultant functions are just some transformation of the parent, I can take the information I know about the parent function and generalize how to find, the domain and range and period and amplitude and all that jazz, just based on the type of transformation occurring. So we can say for a parent function sine or cosine with the corresponding resultant functions, the domain still going to be all real numbers. The range is going to change from -1 to 1 to k minus the absolute value of a to k plus the absolute value of a. The amplitude is going to change from 1 to the absolute value of a. The midline is going to change from y equals 0 to y equals k. The period from 2 pi to 2 pi times the absolute value of c. And then the frequency from 1 over 2 pi to 1 over 2 pi times the absolute value of c. This stuff right here would be stuff you'd be well served memorizing, or prime candidates for your note card. This is information you'll use frequently throughout the chapter. Again, it's easy to use. It's just filling stuff into a formula. But if you're not a good memorizer, for sure that's something you'd want to put onto your note card. And I'm going to try to do a better job here as we go of highlighting the stuff that I would put on my note card. Maybe that way when I give you the time in class to make your note card, more than one or two of us will finish a note card in class. Because you could conceivably have, done everything but your example problems on your note card to start, right? Okay. Let's do a couple of examples now. So this example says, given the parent function f of x equals sine x, find the transformations for the resultant functions, and then list the function's domain, range, amplitude, centerline, period, and frequency. Centerline and midline get used interchangeably. They mean the same thing. So the first thing I need to do any part of this example problem is to figure out the values for A, C, H, and K. Now, I know the general form for any sine function is the form of the resultant function. And just from the way things are written, I can really easily see that A should be -4, that K should be 1, but I got a little work to do to kind of figure out what the C and the H is, because the way this is written, it doesn't look the same as my general form for the resultant, right? So I notice that there's nothing being added or subtracted to my 2x. So hopefully it's pretty easy to see that the H should be 0, right? But how do I write 2 as 1 over C? We did this last time. How do I write 2 as 1 over C? What would the C have to be? Good. A half, right? Because I know that 1 over 1/2 is the reciprocal of the reciprocal, which is the same as doing nothing at all. So the reciprocal of the reciprocal of 2 is just 2. So 1 over 1/2 is the same as 2. So now it should be quite clear that my C is 1/2 and my H is 0. Is everybody okay with how I came up with the values for A, C, H, and K? Too rowdy over there. Again, how often are you going to have to do this skill of figuring out the values for A, C, H, and K to do problems in Chapter 3? The answer is all the time. If you don't feel good about this skill, it's going to be a long chapter. Please come and get some help before you realize the day before the test that, like, I'm hopelessly lost. More. Well, because if I 2x, I can just think of as 2 times x minus 0 still, right?
Oh, okay.
That's all I'm doing. Is that okay?
Yeah.
So just kind of like, well, there's nothing added or subtracted, so I can just throw a minus 0 in there. It doesn't change anything, you know? All right. We're cool? Be good at this skill. I promise it'll come back and be The time you spend getting good at it will be worth it. All right, so now I'm going to describe my transformation. How am I going to do that? I'm going to use the same criteria that we used in last time. So this list that we said we should put on the note card, I've memorized because I've been doing this job for like 15 years and I've probably done this problem literally thousands of times in my life. So I have this all memorized. You're doing it for the first time. You don't have it memorized yet, most likely. Hopefully by the end of chapter 3, it's like I got it memorized because I've done it so many times. But if you haven't, this is what I'm looking at to do what I'm about to do. Okay? It just looks easy because I've done it so many times. All right. So my C value is 1/2. Since that's positive, I know I don't have any reflection across the y-axis. The absolute value of my C is 1/2. That's less than 1. So I know I have a horizontal shrink by a factor of 1/2. My A value is -4. Since that's negative, I know I have a reflection across the x-axis. The absolute value of my A is +4. Since that's greater than 1, I have a vertical stretch by a factor of 4. My H is 0. Since it's 0, I have no horizontal shift going on. And my K is equal to 1. Since that's bigger than 0, I know I'm going to shift up 1 unit. No, right, I wrote a K there. That should be a 6. That's crazy, Mr. Kulik. How did you learn to count? 1, 2, 3, 4, 5, K. I don't know. It's the end of the day. So that's me describing the transformation. Exactly the same process that we used in the last assignment, right? Nothing has changed other than there's a sine or a cosine in there, but like, what did it do? It doesn't really do anything. All right. The other thing it asked for was domain, range, amplitude, midline, period, and frequency. The domain, if I go back and I look, is always all real numbers. Doesn't matter what the transformation was. It was all real numbers before. Doesn't matter how I stretch it or shrink it or rotate it or whatever. Domain's still going to be all real numbers afterwards. I shouldn't say rotate. I meant reflect. I even write always next to it. The range, we're told, is K minus the absolute value of A to K plus the absolute value of A. So for us, K was 1, and the absolute value of A is 4. So our range goes from -3 to 5. The formula for amplitude, it says, is the absolute value of A. So that's the absolute value of -4, which is just 4. Maybe I'll box some of these things up. Maybe I'll use a different color to do the box. I'll draw it at the end. The midline is y equals k. The k in our situation is 1, so it's y equals 1. Now I want to be clear about something with these midlines. When you write on your paper the midline, you must include the y equal, or I will mark it wrong. The midline is an equation for a line. It should start y equals. If you write just the number 1, I am going to mark it wrong because it is the equation of a line, the midline. It's not a number, it's not a length or a measurement or a ratio that doesn't have an equation built around it. It's the equation of a line. It needs to start y equals. Okay? Just to be clear. The period, we find that by doing 2 pi times the absolute value of c. The c in our problem was 1/2. 2 times the absolute value of 1, or 2 pi times the absolute value of 1/2 is just pi. And the frequency is just 1 over the period. So in our case, it's 1 over pi. I'll box with a different color so it stands out. Everybody's okay? Do we feel like we need to do another example of this, or is this okay, right? Nothing really different than last time other than plugging these things into formulas, and it's like, yo, Mr. Kulik, I can look at the formula and plug the stuff in. I'll be all right. All right. Let's move on. Let's move forward then. So what we're going to talk about next is going to be graphing. So recall from last time, what we did is we said, okay, we have some parent function with points x, y, and we do some kind of transformation to it to turn it into a resultant function. And the way those points get transformed is we do c times x plus h and a times y plus k, right? And again, we said last time, this is something you should memorize or at least put on your note card. I'll just reiterate that again. Is that is certainly a note card thing. The question we should be asking is, what points should I be using for sine and cosine, right? Okay, so those, I have some points and transform them using that map. Okay, that's fine. Same thing that we did in the last chapter or last lesson. But what points should I be using for sine or cosine or whatever? Well, let me draw your attention to this sheet in the OneNote labeled trig reference points. So the points that I'm going to use as the points for my parent function for sine and for cosine listed right here. So every time I'm graphing a sine function, these are the points I'm transforming. Every time I'm graphing a cosine function, those are the points I'm transforming. Are these something that you need to memorize? No, I'll give these to you. Okie doke. All right, so let's do an example, because at this point it's the same as what we did last time, right? Let's just see it in action. Make sure we got it. Yeah, it's fine. All right, let's say we want to graph y equals -3 times sine of, 2 pi. That's dumb, Mr. Kulik. You need an x for it to be in a line. 2x minus pi over 2 plus 1. What's my first order of business going to be? I need the values for a, c, h, and k. Is this getting redundant yet? It's okay. Almost every problem we're doing in this chapter, we're going to be concerned with those 4 values, and those are either going to be the key to how to do it or just the point of doing the problem. Everybody's okay? So again, we know that the general form for a sine function is this. Right away, I can see the a should be -3. The k should be 1. But I'm going to have to do a little work to get 2x minus pi over 2 to look like 1 over c times x minus h. Everybody agree? Okay. So let's start down that path. Oops. So I notice that the coefficient on the x is 2. So I'm going to start by factoring a 2 off. When I factor a 2 off of the 2x, it just becomes x. But when I factor a 2 out of pi over 2, what does it become? You guys should be able to answer this question. When I'm factoring out something, what operation are we doing? If I had like 2x minus 4, and we write this as this, what did I do to get the 2? Well, we're doing the opposite, right? We started here, and we ended here, right? What in my head did I do to get the 2 at the end? What math did I do in my head? I took the 4 and I divided by the 2, right? Everybody agree that that's what you did in your head? So what are we going to do here? We're going to take the pi over 2 and divide by 2. What's pi over 2 divided by 2? Let me ask you an easier question then. What's 1/2 divided by 2? Okay. From your giggles, we'll go back to elementary school. So the rhyme that my teacher taught me to divide fractions. Dividing fractions is easy as pie. Flip the right and multiply. So this becomes 1/2 times 1/2, or 1/4. Dividing fractions is the same as multiplying by the reciprocal of the divisor, right? I've broken more, it looks like.
Is the equation in the red on top the original equation?
No, it has nothing to do with the original.
Oh.
It was just trying to get you guys to answer my question by asking something a little easier.
Okay, I was getting confused.
No, this has nothing to do. This is like a total aside. Nothing to do what we were working on, other than it was like, I was trying to get you to answer a question about what we were working on. Everyone looked at me like I had a second head growing out of my neck. I said, okay, let me ask you an easier version of the question I'm asking you, where there wasn't a fraction involved. Okay. So keeping in mind that 1/2 divided by 2 is 1/4, what is pi over 2 divided by 2? Very good. Pi over 4.
Wait, how are we getting pi minus pi over 4?
So I took pi over 2 and divided by 2.
Okay.
Because I'm factoring the 2 out, right? The act of factoring out is dividing. So 2x divided by 2 gave me the x. And then pi over 2 divided by 2 gives me the pi over 4.
Okay. So we just distributed the two out?
Factored the 2 out. Distributing would be multiplying it back through. Factoring is dividing it out to put out front
Oh, thank you.
from a vocabulary perspective. So now that we've done that, how do I write 2 as 1 over c? Thank you. Somebody was paying attention earlier. Even though our head was down, we were still listening, which is great. No, it's fine. I get it. It's the end of the day. The lights are out. I can listen without watching. It's okay. I'm not trying to accuse you of anything. I'm just pointing out that apparently it was working for you because you absorbed the point from before. Okay. So we can now see that the C is 1/2. And the H is 1/4. So that's everything, right? C is -3. I'm sorry, A is -3, C is 1/2, H is pi over 4, and K is 1. Okay, that's my first step, is getting that information. That's the first. Well, here's the Maura. Here's the good part. It's easy from here. This is the worst part, I think. Okay.
This is the word I think you're right. I got like the gist of it.
So now I'm going to write my transformation map. So I'm just going to plug those numbers into my formula. Everybody okay? Yes. Absolutely. So all I did was plug my A, C, H, and K into that formula, right? So far, so good? That was easy, right? Now I'm going to go and look at my reference points sheet and copy down the 5 reference points for sine. Now, Mr. Kulik, again, has done these problems like thousands of times in his life and has these all memorized. That's not an expectation for you.
Will we be like given these, or should we put them on our next card? Oh,
So again, those points are just coming from the reference point sheet. Why did I choose those ones versus any of the other ones on the sheet? Because the function we're graphing is a sine function. So I needed to pick the reference points for sine.
Oh, there are 3 different sets. So they're like broken up for us. It'll tell us what's what. Sorry. Oh, perfect.
Tangent just doesn't exist anymore.
It does. It's down there. We just aren't talking about it yet.
Oh, there's more now.
There's more.
But will it always tell us what to use, or do we have to figure that out?
Here's where it'll tell you.
Oh, in the perfect.
Right in the problem, it'll tell you which one you're using. It's okay. It's your first time doing it. It's okay to ask the questions and have it be an obvious answer. It's fine. No big deal. Right? Ask the question before you get to it. All right. So now what do? All I'm going to do is plug my x, let's say into the x in my formula, and then my y into the y in my formula, and evaluate. What's 1/2 times 0 plus pi over 4? Great. And what's -3 times 0 plus 1? 1. There's my first point. And now I'm just going to
Oh, so are we always using 1/2 and then pi over 4? And then just plugging those in parentheses next to it?
I'm just, every time I'm plugging into the x and plugging into the y. Yep. So what is 1/2 times pi over 2? Excellent, pi over 4. And what's pi over 4 plus pi over 4? Not 2 pi over 8. 2 pi over 4, which reduces down to pi over 2. And then what's -3 times 1 plus 1? Nope. -3 times 1 plus 1.
Oh,
-2. -2. I know. What if you have poor fraction confidence?
Calculator?
You could use your calculator. To get your calculator to do this, though, what do you have to do? You have to take out the pi. So if and then we can put it back on when we're done, yes. So I could do 1 over 2 times 1 over 2 plus 1 over 4.
Oh, why can't we use pi?
Because the calculator can't put an irrational number into a fraction, because by definition pi can't be written as a fraction. So the calculator is going to really struggle with that piece. But if you just take the pi out and then put it back as pi over 2 when you're done, everything is fine. And the calculator is happy, and you're happy because you didn't have to add the fractions. Okay? Let's do the next one. So how is this so far? This next step is still pretty easy, right? All we're doing is plugging something into a formula and then evaluating it. Now, sometimes the arithmetic can be a hassle, but it's like the difficulty is low because all we're doing is plugging something in and evaluating. All right, so if I do 1/2 times pi, what do I get? Great, pi over 2. And if I add pi over 4 to that, what's 1/2 plus 1/4? 1/2 plus 1/4. 3/4, right? If you take 50 cents and you add 25 cents to it, it's 75 cents. That's 3/4, right? So that's going to be 3 pi over 4. You can use your calculator if you need to. It's fine.
Like when people at the register check you out and they're using their phone calculator, I'm like,
Yeah.
oh.
Yeah, of course.
Okay, I get nervous.
Yeah.
Yeah, can you get nervous? I don't know.
Look, it's okay if you want to use your calculator to do this. I'm not judging you. I wouldn't have shown you how to use your calculator if I didn't want you to do it. What I want to do is I want to remove all the little like hurdles of stuff that you should be really confident with that maybe you're not, that are getting in the way of doing this new skill, right? If you get something wrong doing this, I want it to be because you didn't understand how to do this, not because you didn't understand how to add fractions. You know what I'm saying?
Yeah.
Okay? Because again, like, we can do this and you've done it a million times, and if you're to some extent like this, maybe it's as good as you're going to get at it, but I don't want you to get these wrong because you're adding fractions wrong. I want you to get it wrong because you didn't understand what we're supposed to be doing. Okay? Well, effort does count, but not all the way. Right and wrong also counts too, but you're right, effort matters. I mean, to a great extent, that's what the homework quiz is. Look at these x values. You guys notice anything happening? Do you see a pattern?
They get bigger.
Okay, by how much?
By a 4.
By a pi over 4, right? So what do you think the next one should be?
1 pi.
1 pi. What should be the one after that?
2.
5 pi over 4, right?
Yeah.
Everybody's okay? Do you see the pattern that Grace was pointing out?
Wait, what's the last for 5 pi?
Yep. We went from a quarter to a half to 3/4, then we'll be at a whole, and then we'll be at 1 1/4, right? Is it easier to just look at the pattern after a couple than to add the fractions? If you feel that way, go ahead and do it that way. You'll get this, you should get the same response. If you're doing this correctly, the x's will all go up by the same amount. Everybody's okay? I'm going to write out the rest of this for us. Okay. So everybody's happy so far? Getting the points? Again, we went really slowly through this, but this, all it was plugging things into a formula, right? Will it take a couple of tries to feel good about it? Probably, but at the end of the day, we're just plugging the numbers into a formula, right? Plug and chug. Well, we have to graph it now. We have these points, right?
It's like not hard. It's so time consuming one of these questions on the test.
You guys will get better at it, and it will go faster. I'm going particularly slow because this is the only example I plan on doing, so I just want to make sure that we're like plodding through it in good, a normal tempo so nobody feels left behind, because I'm not trying to blaze through 10 of these examples.
It's like fun when you get it, but like,
Yeah.
that's how I feel. And like I just don't get it, then no, I just don't get it.
All right. So if I'm going to draw my own x-axis, how far apart should I put my tick marks?
Not that far. Oh.
What? Who said it? Quarter pies. Yes. Why pi over 4s? What's the difference between all the x coordinates here? They're going up by pi over 4, right? So I'll have 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, and then negative quarter, negative half, negative third, negative pi. Okay. So let's now plot some points. So I have pi over 4 and 1. I have pi over 2 and negative 2. 3 pi over 4 and 1. Pi and 4. 5 pi over 4 and 1. Everybody okay? But what if I said that I want you to fill the space that's given? What would we do? I'm just going to kind of continue the pattern, right? So I'm going to pretend that this spot is here. So how did I get from the green circle to the next spot? I went 1 unit over and 3 units down. So I'm going to go 1 over and 3 down. Now I'm like here. How did I go from the green box to the green circle? I'm going to go 1 unit over and 3 units up. Now I'm here. So to go from the green box to the green circle, I'm going 1 unit over and 3 units up. Yes, we also have to do it the other way.
Sorry.
It's like I wouldn't have said it if she didn't ask. Of course I was going to do it. It's not her fault. All right. So now we're like going backwards, right? So I'm going to go 1 unit left and then 3 units up. 1 unit left, 3 units down. 1 unit left, 3 units down. 1 unit left, 3 units up. 1 unit left, 3 units up. Okay. Everybody's all right with what I did there to fill the space? Notice I didn't generate any new points. I didn't apply the transformation map. I just used the pattern of what I'd already graphed and just kind of continued the pattern, right? On your test or quiz, if I ask you to graph something and fill the space, I expect to see the points plotted. I don't expect to see a coordinate for the ones that you've extended, but I do like what I've drawn in green, where it's clear where the point is. I expect to be able to see the point, and then you kind of connect things through, right?
So technically just like copying it over?
Yes, I'm just continuing the pattern in both directions.
So I can kind of just like...
You just use your eyes.
Oh, perfect.
We don't need a plot.
So I can just like wing it?
All I'm doing is like 1 down or 1 over, 1 down. 1 over, 3 up. 1 over, 3 up. And I'm just following the pattern, and you have to place a point in the correct location, but you don't have to show any work for me. You can just use your eyes and do some counting of boxes. That's what I'm telling you. Okay, so this problem is done. So on your homework, when you do the graphing, I need to see this work. I need to see how you're getting your resultant, your transformed points. And then I need the extended, once you plotted them, I need the extended graph. Okay? So your assignment for next time, is this chapter 3 worksheet 1. So the first questions we ask for the amplitude, period, frequent or midline frequency, and then to describe the transformation. So just like that first example we did, right? So you have some of those, and then we have some graphs. When I have a blank for A, M, P, and F, what do you suppose those stand for? Amplitude, midline, period, frequency. Correct. So you're going to go ahead and do that and draw the graphs. Make sure you extend to fill the space. Pay attention to the labels on the axes. So like this line here, what would this line be? Pi over 2. Pi over 4 then would be like halfway between 0 and pi over 2. And 3 pi over 4 would be like halfway between pi over 2 and pi, right? Everybody's okay? So you have, I think, 6 of these graphs. By the end, you should feel good about it. Keep in mind, they're going to be switching between sines and cosines. So when you're pulling your reference points from the sheet, be paying attention when it changes from sine to cosine that's using the correct reference points. But that's it. Okay? Not much different than what we did last time, right? That's it. I'm done. I'm going to stop there.